Hello and good morning, dear students. We'll start the meeting in another few seconds.
Hello, sir.
Hello.
Sir, where will we upload PDFs?
What PDF?
Classes.
Material, is it?
Yes.
Material will be generally sent to the DSU authorities. The coordinator is Dr. Abida. So we'll all be sending to Abida Dodamani, and from she is the one who actually distributes to all of you. Okay. Soon after my class, I generally do it. So please find out from her, and you will get actually a better idea.
Okay, thank you.
Write to them. I think they are the ones who are managing the material, but we will send it immediately after the class. Okay. Great. So today I'll be looking at the second year topics. All right. Second year topic. The first one that I'm going to look at is the electric charge and fields. And in the next class, I'll look at the potential, and then after that, I will do capacitors, then current electricity. So that way. All right. So now, today's class, I'll be just give me a minute. Just give me a minute. Okay. It's about electric charge and field. So let's try to look at some of the important points here, and then perhaps we will start solving MCQs. First thing is about the charges. Now there are certain properties of the charge you should be very, very well aware of. What are the different properties of charges? Number one, okay, this is a very important chapter. Any of the competitive examination that you think about, and I don't know why you always insist on the number of marks. Please ask the number of questions. Okay? Each exam will have different marks, so don't worry about that, but rather worry about the marks that you get. That are generally coming around is 3 to 4 questions every time. Okay, on this chapter itself. I'm not talking about the charges, by the way. It's about the chapter. You will get at least 3 to 4 questions easily. I don't know whoever is interested in only knowing the number of questions in the examination. I'm so sorry. Now worry about the concepts first, because I can always ask questions which have not come until now. By the way, dear students, I am allowing you to all unmute only because I want you to interact with me. I can always take away that right if it becomes a nuisance. Make sure that you all are very judicious in using this facility. Okay. So please mute whenever there is no questions. When you want to interact, only then you can unmute. All right. Thank you very much. Now, what are the different properties of charges? You all know that first one is there are 2 kinds of charge. 2 kinds of charge, positive and negative. Positive charges. So I will always say that like charges repel, unlike charges attract. Okay, because we are revising, let's revise everything. Second one is for me, which is very important, is there is what is called quantization of charge. Quantization of charge. That is, Q can be written as N times E, where E is 1.6 into 10 to the power minus 19 of a coulomb, and N is the number of such electrons. This always will be an integer. Will always be an integer. Okay. Now at this point, you should also know that lack of electron, okay, will give rise to positive charge. We call this also as deficit of charge, the deficit of electrons. Excess of electrons will give rise to negative charge. Now, the whole charging idea can be understood in that way. See. You have what is called as conservation of charge. Conservation of charge. I'll tell you about where is the disturbance? I don't see any disturbance. Where is the disturbance? Which I'm not hearing, only you people are hearing. Is everyone having some disturbance? Can someone tell me? Is my voice clear to all of you? Am I audible? Am I audible?
Yes, sir.
Okay. See, again, this facility I'm providing to unmute only with an understanding that you will all behave very, very responsibly.
Yes, sir.
Mute now. All of you mute. All of you mute. So the conservation of charge, which actually says that charge before a process will be equal to the charges after the process. After the process. Remember, charges can be created, charges can be destroyed. That's not the idea. Charges before the process equal to charges after the process is the conservation of charge. So please make a note. Charges can be created and charges can be destroyed. Both are possible. That's not conservation law, but this in fact is what the conservation law is all about. Where are the charges getting created? In what is called as pair production. Pair production. A gamma ray comes and produces electrons and positrons. Okay. Where will the charges get destroyed? In what is called as annihilation process, where electrons and positron both put together will give rise to gamma rays. So the electron is lost, positron is lost in this case. In the first case, electron is gained, positron is gained. So you have one minus charge here obtained and one plus charge here obtained. So charges can be created, charges can be destroyed. Okay, but that's not the conservation law. Conservation law is about charges before the process equal to charges after the process. Okay, if you all have written down this, I'll go to my next page and go to the next idea.
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
This
Yes, sir.
charging a body. Now, how do you charge a body? There are three methods you all are very, very familiar with. The first method is the method of friction. Where you consider two Ganesh, mute. Two suitable material, and these two suitable material should be such a way that one should give electrons, the other should take electrons happily. He should give electrons happily and they should take electrons happily. So therefore you need to choose such kind. Now these two such suitable materials, there are plenty of examples. Glass and silk. Glass is ready to give electron to silk. As a result, this will become positively charged, silk will become negatively charged. Okay, same way. You also have fur and amber. In fact, electron has got the name from the amber. Amber in Greek is called actually as electron, and therefore they have called it that way. Then you have rubber with wool. Again, rubber is ready to give electrons, wool is ready to take electrons. So this will all become positively charged, this will all become negatively charged. Okay, so this is the method of friction. You rub one against the other, suitable material, these are the ones. And there can be questions directly on this itself. There is one person who is always interested in number of questions. Note this. This can be a definite question. So make a note of this. For you, this is important. For me, all questions are important. Next one is by conduction. Now the method of conduction here, what happens is, you take one material which is already charged. Okay, already charged. And another material which is neutral. Now these two are brought in contact. Let's say the first one actually has a radius A, the other one which has a radius b. So the initial charge, let us call it as q. And then if you bring this another body also in close contact with this body also will now acquire charge. The charge on this, let's call it as q1, charge on this, let's call it as q2. It can be shown that q will be equal to q times b by a plus b. Okay, q1. q2 will be equal to q times a by capital Q times a by a plus b. You can actually show this to be equal, because the charge flow will happen until the potentials are the same. So therefore, this condition is quite a valid condition. Just hold on for a minute. KQ1 by I think this should be A. I'm so sorry. This should be A. This should be B. I have wrongly noted down that. Yeah, this should be QA by A plus B. This is QB by A plus B. Are you all okay with this? I'm sorry about this. I think I just wrote down this in the other way around. The last method, in fact, is called as the method of induction. The charging by induction. Now, what happens in the induction? The most important point to notice: if you bring in a body which is positively charged, the other body, number one, has to be placed on an insulating stand, and this should be connected to ground. Connected to ground, then there will be an induced charge on one end, or negative charge on the other end. There will be positive charge. All this positive charge will flow to the ground, and then if you remove the grounding and the object, this will now become negatively charged. The whole thing will become negatively charged. If you start with a charge Q, this also will be minus Q. The magnitude is the same. It's minus. Only the minus is there, but the magnitude, remember, is going to be Q. If you start with say 2Q, this will also be 2Q. So therefore, the magnitude will remain the same in the case of induction, but the opposite charges are generally obtained. So there will be an equal and opposite charge induced in the body. Okay, so this is going to be an important idea. Can I go to my next part? If you are written down this, can I go to my next page?
Yes, sir. Yes, sir.
Good. Tell me now, what is the next thing that we generally study in case of electrostatics? Will be the famous Coulomb's law, isn't it? The famous Coulomb's law. Now, what does this law tell you about? It tells you that the force between two charges, Q1 and Q2, separated by a distance R. Okay, if it is like charges, then they repel. If they are attractive, if there are unlike charges, they get attracted towards each other. Let the separation between the two be equal to R itself. Now, according to Coulomb's law, the force is given by, for both of them, K Q1 Q2 by R square. K Q1 Q2 by R square. And also it says that force will be along the line joining the two charges. So it's something which is important for you all to note. And here K is a constant which would depend on the medium. So K is generally given as 1 by 4 pi epsilon naught, and this epsilon naught is called as the permittivity of free space, and its value is given to be 8.854 into 10 to the power minus 12 in the SI units, whatever that unit is. Okay, in the SI unit, this is what it is. First note. And the second note. Here itself, let me also tell you that 1 by 4 pi epsilon naught will actually have a value of 9 into 10 to the power 9. Very easy to remember. 9 into 10 to the power 9. Okay, this will be in, this entire thing will be in vacuum. All this is corresponding to vacuum. In other mediums, K will actually have a value which is 1 by 4 pi epsilon naught epsilon r. Epsilon r is called as the relative permittivity. Relative permittivity. This relative permittivity will be greater than 1. Equal to 1 also in case of vacuum, of course. Okay. In case of vacuum, it will be equal. Otherwise, it's always greater than 1. Greater than 1. That's an important point to note here. The second point, can I go to my next page so that I'll have enough space to write down? Can I go to my next page?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Thank you.
Yes, sir.
Thanks. I just wanted 1 or 2 responses here. But the third point is, if you have 3 charges instead of 2, okay? What is it, Karthik Pujara? What is it that you want to tell me? You have something to ask, Karthik Pujara? F1 and F2. So the Q0 is going to experience charge F1 and F2. Now, how do I find the net force on Q0? This net force on Q0 will be equal to simply F1 plus F2. This, in fact, is called as the principle of superposition. So principle of superposition is an important idea in electrostatics, and we'll be using it. Now, since we have come to this point, let us say that these two makes an angle theta. So on Q2, if I try to draw the free body diagram, I'll have F2 in this side, F1 here, making an angle theta. All right. Now the resultant force will always be given by this angle. Let's call it as alpha. So now what is Fr given by? Fr will be equal to root of F1 square plus F2 square plus 2 F1 F2 cos theta. F1 F2, very important relation. Tan alpha, on the other hand, will be written as F2 sin theta divided by F1 plus F2 cos theta. F1 plus F2 cos theta. Now, some standard relation in this case, which will be directly useful for your examination. Okay, the one who is interested in number of questions, look at this. Will be direct answers for your questions there. F1 equal to F2. Then the resulting force will be written as theta is equal to 90 degree. Okay, then I have root 2 times F. Okay, now B, if theta is equal to 60 degree, then Fr will be equal to root 3 times F. It can be shown. Okay, not very difficult, but I don't want to show that now because lack of time. Theta is equal to 120 degree, then Fr will be equal to F itself. Resultant is equal to F. Both cases, theta is equal to 90 degree, then Fr can be written as root of F1 square plus F2 square. That's how I've taken basically here F1 not equal to F2. In this case, I can always show that Fr will be equal to this. This is the standard relation that I'll be using it. I'm going to take rights to unmute later. Mute whenever you don't have any questions to ask. I don't want to hear all the other sounds of your kitchen, bathroom, and all that. Okay. Let's now look at the next point in the Coulomb's law. Coulomb's law is one of the most important ones, so let's look at that carefully. Here, the next point that I want to make, I forgot the number though. What is the number? Third one is over, so fourth one. So fourth point to note is the vector form. We did this in the case of Coulomb's law also. I mean the gravitation also, right? So same thing, we'll also do it for the case of the Coulomb's law. Let's say that I have two charges here, Q1 and Q2, at a position of R1 and R2, then you have this to be given as delta R, delta R. You will find that the force on Q1 will be like this, F1. Force on Q2 will be like this because it's a repulsive force, F2. It can be shown that F2 will be equal to K Q1 Q2 by R2 minus R1 divided by R2 minus R1, the whole cube. I had seen this question coming many a time. So written in the vector form. Then similarly, F1 can be written as K Q1 Q2 into R1 minus R2 divided by R1 minus R2, the whole cube. Okay, look at this F1, R1, F2, R2. So that will be the first term there. Okay, then you get the expression for both F1 and F2 in this way. This is the vector form of Coulomb's law. Okay, important I would say. Lot of problems in fact get asked in this chapter. Okay, one of the most important for your competitive examination. And therefore, I would also like to take up some examples now on this, which I will call it as the problem types. I told you this is one of the most important part of our discussions. I've been telling you about this problem types. This is the first one. The first problem basically will be on finding the resultant force. The resultant force because of two charges, three charges, and so on and so forth. Look at this. I have charge here Q1, Q2, and Q0. So I have to find out what the resultant force is. For example, it can be on this Q2. So let's call this as Q3, all right? So Q2, and there'll be two forces. One here, I'll call this as F23. The other one here, I'll call it as F12. And if this makes an angle theta here, whatever the angle theta here, the same thing will be theta here. And you know how to find out what FR is, and you also know what should be the resultant of this FR with respect to this. So tan alpha. I have already given you the expression for it. So this can be one of the most important types of problem generally asked here. The second one is, the second kind of problem that I find generally will be on equilibrium problems. Equilibrium problem. Very interesting cases do come in this part also, equilibrium problems. The first one is this. I have a charge here Q, another charge 4Q, separated by a distance, let's say D. Okay, now I have to find a point, okay, where if Q0 is placed, it will be in equilibrium. So where should I place the charge so that Q0 will be in equilibrium? Let's say that I'm going to place it at some point here, Q0, the distance x from here. So what will that x be equal to? Now there is an equilibrium because the force due to the charge Q and Q0, let's call it as F1. Because of 4Q and Q0, there's a force here F2. F1, when it is equal to F2, then we say that Q0 will be in equilibrium because the net force on that will be equal to 0. Now, where will that happen? Okay, that will happen when you have both the forces are to be same. So you can write as K Q1 Q0 by Q by Q0 by x square to be equal to 4K 4Q Q0 by minus x the whole square. Now you can cancel off 4 Q0 Q0 from here, K from here. So what are you left with? You're left with d minus x the whole square is equal to 4x square. Dear students, this is going to be an important kind of problem. Okay, those who are interested in knowing the problems for the examination, this is one perhaps an important one. Take the root on both the sides. So d minus x will be equal to 2x, or simplify this, take x to the other side, then you get d to be equal to 3x, or what is x equal to? D by 3. So where should you keep the charge so that it's in equilibrium? You should keep it at d by 3. D by 3. And also you should also note that to make the entire system in equilibrium, not just Q0, okay, entire system in equilibrium, that is to say, force on Q and 4Q should also be 0, 0. What are the conditions for that? That condition again is very simple. You should make the force on one of them to be 0. Take for example the force on Q. So Q0 is there, Q is there, and the other one is 4Q. So what is the force on this? Force on that will be equal to KQ Q0 by x square plus K4Q Q by d square. Okay, and that should be equal to 0. So that would mean that when you actually have a condition like this, then it would really satisfy. So K, what do I get this to be there for? K is gone. So Q0 x square will be equal to minus 4 Q square by d square. 1 Q also will go away. Okay, one also will go away, and hence I get the expression here to be equal to Q0 to be equal to minus 4, okay, x square by d square. But what is x? X is nothing but d by 3, isn't it? D by 3. And therefore substitute that and you get the expression for Q0 to be simply equal to minus 4 by 9. I forgot Q, I'm so sorry, into Q. So what is Q0 equal to? Minus 4 by 9 Q0. Okay. Yeah, fine. So this will be the expression for your Q0. If this is the Q0 equal to, then the entire system will be in equilibrium. Entire system will be in equilibrium. Okay. I will not have much time, but still I will repeat now. I'm basically trying to see for the set of 3 charges, when will the charge Q0 be in equilibrium, and also when will the entire system be in equilibrium. So Q0 will be in equilibrium when you place it at x is equal to d by 3. Now after you place it at d by 3, you can choose the charge in such a way that is equal to minus 4 by 9 Q. Then the entire system, remember, will be in equilibrium. Remember these 2 values. One is for equilibrium of Q0. The other one is the equilibrium for the entire system. So these 2 will together will be able to help you a lot in the problem solving.
Excuse me, sir.
Tell me, please.
So why haven't we considered force between Q0 and 4Q?
Yeah, you can do that. You will get the same condition. You can do that.
Yes,
Take it as a homework and do it. You get the same condition.
Okay,
Can
sir.
be done. Okay. Let me go to my next page and then look at few interesting aspects again here now. What is the next problem type that I can think of? The third one is if I have, say, 2 charges. This is again another type of problem which keeps coming. So therefore, I'm stressing on this again. And also gives a very important concept. Let's say that I have 2 charges here, Q, and I place another charge Q0 here. Q0 here at a distance y on the perpendicular bisector. on the perpendicular bisector. Let's take this as D. These two values as D. Okay. Then I can show you that the force between these two charges to be equal to K Q Q naught Y by x square, sorry, y square plus d square whole to the power 3 by 2. Unfortunately, I can't really derive all these expressions here because of lack of time. The force will be given by this. What is the direction of the force? The direction of the force will be in this way. F will be in this direction. The net force will be like this. Not very difficult to comprehend because you have two forces. The horizontal components will cancel. The vertical component will add up. Okay, if I call this as F1 and this also as F1, so this will be F1. If I call this angle as theta, this angle also will be theta. So this will be F1 sine theta. This will be F1 sine theta. They cancel off. What adds up essentially is 2F1 cos theta. That is what is actually giving you all this. That is precisely what is actually responsible for this expression. K Q Q naught Y by this. Okay. Now what happens if it is a negative charge placed at that point? What happens if it is a negative charge placed at that point? Okay. You'll find that if you place a negative charge at the perpendicular bisector, then the force will be towards this point. Okay, towards this point. Now this is the midpoint of this. This is a perpendicular bisector, isn't it? So this is a midpoint of this. At this point, when it comes, remember, so F will now be equal to minus K Q Q naught Y by Y square plus D square whole to the power 3 by 2. When it comes to this point, you take Y is equal to 0. And therefore, F also will become 0. F also will become 0. So this will be an equilibrium point. And the force is pointing toward this equilibrium point. Okay. So I can therefore say that since you have a force pointing towards equilibrium, you can get oscillatory motion. Okay. If y is small, that is y is small when compared to d, you can show that the time period of the oscillation, t will be equal to 2 pi root of m d cube by k q q naught. Very simple expression where m is the mass of q naught. Okay, the charge is there, no? So mass of that charged particle is given to be q naught. So this will be the time period of small oscillations. Remember this expression again will be useful for your NEET examination or mains examination kind of. PET sometimes also can be asked such questions. Okay. If you all are okay with this, I'll go to my next page and go to the idea of electric field. Can I?
Yes, sir.
Yes, sir.
So now the concept of electric field. Electric field, you all know, is defined as force per unit charge. Force per unit charge. Or this will be equal to F divided by Q naught. The proper way of writing this would be with a limit. Q naught tending to 0. So this will be the actual expression for the electric field. Okay. Though they tell you that it could be simply F by 1 coulomb, but the actual expression is this. Maybe I'll write it properly here. Limit Q naught tending to 0, F by. This in fact is the expression for the electric field. for the electric field. Okay. Now we shall consider what will be the electric field due to a point charge. Point charge. If you have a point charge Q here, then at a distance r, the electric field is given to be kq by r square. And how is that electric field? In this way. If you have a minus q instead of plus q, then you will have electric field towards this at a distance r. So now E electric field will be equal to minus kq by r square. Minus kq by r square. So electric field actually is again a vector similar to that of the force, and the direction of the fields for the two cases I have shown you here. Now similarly, electric field due to a ring is important. Now what is electric field due to a ring? Is if you have a ring which is positively charged here like this, then the electric field on its axis at a distance x, okay, let's take the radius to be r and charge to be q. Then the electric field can be shown to be kqx by root of r square. I'm sorry, I think I will erase this part. Yeah, will be r square plus x square whole to the power 3 by 2. This is the expression for the electric field on the axis of a ring. Other electric field we'll do little later. Okay, these are the two things that I thought I should tell you about definitely. Okay, and now what are the important problem types in the case of the electric field? So the first and the foremost I want to consider is, if I have the charges here Q and let us say another charge Q, then they'll ask you where will the electric field be equal to 0. So where is electric field equal to 0? You will find out that for a case like this, it should always be at the midpoint. At the midpoint, the electric field, because of each of them, will cancel to give you the net electric field here to be equal to 0. All right. So this is how I find out the net electric field. So this is an important point to actually remember. Now, similarly, if I have a triangle, all corners having charge Q and sides are given to be A, so this is an equilateral triangle. Now in this case, where will the electric field be? 0. Where is electric field equal to 0? You will find that electric field will be 0 exactly at the centroid. At the centroid, the electric field will be equal to 0. This again, finding the position where the electric field 0 is important, and you should know this. If you know, you can directly answer that in the question. You will be very quick in answering that. Same way, another important type of problem is, if I have actually a square here of side A, and I place the charge Q at all the corners, same charge Q at all the corners, then what will be the electric field at the center? At the diagonal again, the electric field will be equal to 0. Electric field will be 0. Same way, if it is a hexagon, you will find that the charge is placed at all the corners, then the electric field basically will be 0 at that point. Electric field will be equal to 0. Electric field will be equal to 0. So I can make a general statement that if you place charge Q at the corners of, at all the corners of a regular hexagon, then the electric field at the center will be equal to 0. Electric field will be equal to 0. That you can be very, very sure of. So this is an important problem kind that you should always know now. The second type of problem which keeps coming in the examination is about the acceleration of a charged particle in uniform electric field. Also a very important problem. You will keep actually getting this problem. So what is it about? So if you have an electric field here and you place a particle of charge Q and mass M, then it will now experience a force F which will be equal to EQ, where the electric field is E in this region. It's uniform. Okay, then this F is equal to MA also is valid, Newton's second law, isn't it? Newton's second law. Now if you equate the two, you will get M into A is equal to EQ, or A will be equal to EQ by M. EQ by M. So the acceleration of the charged particle is given by EQ by M. EQ by M. This is a very important idea, and you will have very interesting questions based on this one. So let me take up two examples for that. The first one is, example in this case is, let us say that I have uniform electric field present in a region like this. A charged particle will enter of mass M with a velocity u along the horizontal direction. If there is no electric field, this charge would have simply traveled like this. Okay. Now, because of the electric field, what happens is this will get now deviated in this way. Okay. I have to find out the position of the particle as it travels. That I have to find out y as a function of x. Okay. I can again show you that the y here will be equal to half ay t square, and that ay is nothing but EQ by M into t square. Now what is this t square about? T is the particle basically would travel a distance x with a velocity u. So x can be written as u into t. So t will be equal to x by u. So substitute that, then you get this to be half EQ by M into x square by u square. So what is the trajectory of the particle? Y will be equal to half EQ by M u square into x square. So y is proportional to x square, and therefore what you will have is a parabola. Going to be a parabola. Okay, this is again time and again these questions are asked, so please be careful about this. I am also looking at what are the possible questions for the mains, not just for the CET. Now let us say that I have an electric field present in the vertical direction here like this. Vertical direction like this. Then let us make sure that the acceleration due to gravity is 0. So everything is done in space. But this actually has an electric field given like this. A charged particle of charge Q and mass M is now projected with a velocity u naught at an angle theta. Then what happens is it will now actually have a projectile motion. Where A will be equal to EQ by M. So wherever you have G, in this case now you're going to have EQ by M. So you will be asked to find out what will be the range of this projectile. The range of the projectile, what is the expression for it? If you all remember, u square sine 2 theta by G. Now instead of G, what I will have is, instead of G, this will be replaced with EQ by M. replaced with EQ by M. All right. So that's how I can actually obtain the range. Same way, if you are interested in finding the time of flight, this will be equal to 2u sine theta by g. Instead of g, write it as EQ by M. That's it. Then you get the expression for the time of flight in this problem. Okay. 2u sine theta by EQ by M. So these are the two problems that I thought I should be telling you about, okay, in this case of electric field. Can I move on to my next one?
Yes, sir.
Sir.
Sir. Yes, sir.
Thank you, sir. Thank you.
Excuse me, sir.
Yeah, tell me, please. Yeah.
Sir, what happens if in between two charges and another charge is placed? How does the electric field depend?
Okay, that's a nice question. So let's take it up. So you have two charges here, Q1 and Q2, and you want to place another charge here, Q2, right? Now I want to find out what is the electric field at some point here, let us say. I have kept this at A, distance A, this at distance B. Now I want to find out at X, what is the electric field given by. Now this electric field will be equal to E1 plus E2 plus E3. Okay, let us see what those forces are. First one is Q2. Between Q2 and this point, the electric field will be like this. So E2 will be in this way. Q1 will produce an electric field that will be E1 also in this way. I think I should say Q3, no, one of them. Make it Q3 then. So Q3 will also produce a charged electric field, but that electric field will be opposite in direction. Can you see that? So E1 and E2 are towards right, E3 is towards left. Okay, so now what are the fields? First, E1 will be equal to K Q1 by A plus X, the whole square. E2 will be K Q2 by X square, because that distance is X. Then E3, remember, is negative. So therefore I should say minus K Q3 by B minus X, the whole square. B minus X, the whole square. Correct? So this is how the electric field is going to be. So this is one idea. Another idea would be now you have Q1 and Q2. Q1 and Q2. Okay. At a distance, then let the separation between them be equal to D. Then at a distance X, okay, what is the electric field? The electric field at a distance X here will be because of Q1 in this way, E1. Q2 will be like this, in this way. So sum of the electric field now will be equal to Q1 minus Q2, where this will be equal to K Q1 by X square minus K Q2 by D minus X the whole square. Okay, this will be the electric field. Now the question is, what happens if I place Q3 at X? Okay, at this point, what happens if I place a charge Q3? Then very simple to find out. It will experience a force. It will experience a force F is equal to whatever the electric field that you obtained into Q3. You already obtained this now. Multiply with Q3, then you get the force on this charge. Force on this charge. Okay, did I answer your question to some extent at least?
Yes, sir.
Okay. I'm now going to my another say problem type here for this itself. If you consider a pendulum, okay, of charge Q and mass M. Now keep this in a region of uniform electric field. Then what happens is this pendulum will now get displaced by an angle theta. Okay, until the equilibrium is obtained. Equilibrium is obtained because of the force EQ, because there's an electric field E, charge is Q, EQ. Mass is there, and therefore there will be mg downward, plus this basically is a string, and therefore there will be tension T. Tension T. All right. You can show that this angle will be theta. So T cos theta will be equal to mg in equilibrium. Now this will be T sine theta, and T sine theta will be equal to EQ. Will be equal to EQ. So under the equilibrium conditions, I can always say that tan theta will be equal to EQ by mg. So problems will be asked to find out what theta is, what angle it will be. Or angle is given, then maybe ask you to find out what electric field is, and so on and so forth. So it's a very important idea, very important method, also for determination of electric field, okay, as a method. This will be useful. So if you all are done with this, I would like to now go to my next page and the next concept in this chapter. And that concept is about the electric flux. Is about electric flux and Gauss theorem. Okay. Now, first of all, let us look at what is the idea of electric flux. Now, the flux comes due to the electric field lines. Electric field lines. Now, for a positive charge, if you have, the field lines will always be going away from it. Okay, we say that the field lines basically will be diverging. This is a concept that you all should know by now. Okay, so the field lines diverge from a positive charge. But for a negative charge, if you have a negative charge, then the field lines generally are towards it. So the field lines are coming towards the charge. So we say that the field lines here converge on the negative. For the case of a positive charge and a negative charge, field lines are going to be like this. The field lines are going to be like this. Okay. They have an important property that if you want to find the field at the point, draw a tangent at that point. That will tell you what is the electric field at that point. So the tangent drawn at different points are going to tell me about the field present on act a little more responsibly, I say. You can't switch on your mic and leave it. No, it's so many students are listening to it. You're unnecessarily creating disturbance for everyone. Now, same way, if you have two positive charges, how will the field lines be? The field lines are going to be like this. So the field lines, because of a repelling field, will always be in this way. Attractive field I showed you in the previous one. Okay. I showed you here. This also will be a field line. But here you will actually have something like this. Okay. So this is how the field lines are going to be for different configuration of the charges. We define what is called as flux. Flux is simply number of field lines passing through an area. An area is called flux. Flux can also be written as integral EDS cos theta. Okay, integral E dot ds also can be written. Now, for the case of a closed surface, the flux will be given by the charge enclosed by epsilon. This is your Gauss theorem. This is your Gauss theorem. Okay, is given by charge enclosed by epsilon naught. Now there are plenty of applications for this Gauss theorem. So the application you would have determined the electric field because electric field is given by for the infinitely charged rod. For infinitely charged rod. For an infinitely charged rod, I'm going to define lambda, which is charge per unit length. I'm going to define this, okay? The amount of charge present here. So this will be simply dq by dl. Hey, come on, yeah, switch off your mic. That XT108, 1068, switch off your mic. You're disturbing so many students, you know, and also me. Now at a distance r, the electric field will be given by 2k lambda by r. And this electric field obviously will be away from it. So you'll find that this will be the electric field which will be present everywhere around this wire in this way. Okay. Let's also look at what will be the electric field because of a shell. Because of a shell, the electric field inside will be 0. Okay, if there's a charge on this, it's a shell means inside will be air or vacuum. There's no material there. Material is only present on the layer here. So it's a charge is Q. Inside is 0. Electric field on the surface is given to be KQ by R square. At a point, capital R, let's say, call it as capital R, so it becomes easier for me to write down the next one. R, at any point here outside will be equal to KQ by small r square. This is capital R square and this is small r square. Small r square. Important idea, please keep it in mind. Next one is what happens in the case of a solid sphere. Case of a solid sphere, what will be the electric field inside? So this is a solid sphere. Electric field inside will be equal to KQR by RQ. Electric field at the surface will be equal to KQ by R square. Outside, at a point here, the electric field will be given by electric field outside will be given by KQ by R square. As if that the whole charge is concentrated at the center. That is how it would behave. Any spherical distribution of charge will always behave in that way. Okay. Fine. Now comes the last bit of this discussion. Okay. I'm going to the next page and writing down this part. The last bit here is about the electric dipole. Now, what are the things to be noted down for electric dipole? Dipole is a combination of two identical charges with one positive, the other one negative. Equal and opposite charges, we say. Separated by a distance d or 2d. Separated by a distance 2d. Now, the midpoint of the dipole is what I'm going to always consider as my reference. And now I will define few things here. I'll make this as minus and this as plus, okay? Plus. Now I'm going to define dipole moment. Now what is a dipole moment? Dipole moment will be Q into 2D. Q into 2D. Okay, is the dipole moment. And what is the direction of this dipole moment? Direction will be always from minus Q to plus Q. So the dipole moment will always be in this direction. So call it as P. Okay, so this in fact is the dipole moment. You will find that the electric field due to the dipole moment will be very interesting to always observe. Along the axis, so second point that I'm looking at is electric field due to dipole. So along the axis along the axis, the electric dipole, remember all measurements are made from the midpoint of the dipole. So let's call it as X. So this is D, this is D. Then the electric field at a point on the axis can be shown to be equal to 2 kp by x cube. Okay, 2 kp by x cube. Electric field will be in the direction of the dipole moment itself. You consider on this side or on this side, both the sides the electric field is going to be along the direction of P. That will not change at all. Both the places electric field is given by this. Now another important point that you will want to know where the electric field has to be obtained is what is called as the equatorial line or the perpendicular bisector line. Okay, the equatorial line here. Along the equatorial line, if you want to consider the electric field at a distance y, you can show that the electric field will now be given as minus kp by y cube. Cube is important. Here it becomes cube. And what does the minus sign indicate? P is along this direction. The electric field will be opposite to that. So electric field at this point will be towards left. It is towards right, no? Here it will be towards left. Towards left. Okay. So now the third point here in the case of the dipole is, if I have a dipole here minus q1 plus q, and I want to find out what will be the electric field at a general point, not on the axis, not on the equatorial plane, but at an axis here, making an angle theta. This is your P, so this is, let's say, called as R. At this point, electric field can be written as Kp by R cube into 1 plus 3 cos square theta whole thing under the root. Whole thing under the root. So this will be the electric field given at that point. You're at that point. Now you will also need to know what is the direction of the field. Now with respect to this line, the electric field here will be at an angle alpha. Okay, and that alpha can be written as tan alpha equal to half tan theta. Whatever the theta here, half of that will be equal to tan alpha. So you can show that the electric field will make an angle alpha with respect to this direction in this way. At a general point. Okay, I'll go to my next page if you all are done with this.
Yes, sir.
Okay, now if you press the dipole.
Yes, sir.
Dipole, yes, tell me. Dipole in a uniform electric field. In a uniform. It will experience a torque minus Q plus Q. So I keep a dipole here pointing like this, making an angle theta. Then this will experience a torque given by minus PE sine theta. Minus P sine theta. Or can be written as, torque can be written as a vector, it's P cross E. P cross E. Now the net force acting on the dipole will be 0. There will only be torque. Okay, it experiences only a torque, no force on the dipole. This will be a case of a uniform electric field. Uniform electric field. Fine. So with this, I think whatever information I wanted to tell you about this problem, I have given you. Next, let us start solving problems on this idea. If you are all okay, can I do that? Can I go to my next this thing on start?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Yes. Let's start doing it. Fantastic question. Okay, a dipole moment of dipole moment P is kept at the center of a ring of radius R and charge Q. The dipole moment has a direction along the axis of the ring. The resultant force on the ring due to the dipole is given by. A little difficult problem, but very, very interesting. The idea is very interesting. So let's see what exactly it says. You have a ring placed here like this. we have done something about the ring also, remember that. And along the axis of the ring, a dipole is placed. So let's place the dipole here like this. P is kept. So a minus charge here and a plus charge here like this. At a distance r, it will always produce an electric field in this direction. Correct? And that electric field, I already know what it is. That will be equal to Kp by Rq. That is the electric field produced. Now, this electric field is produced almost at every point on the ring, because every point on the ring is on the equatorial plane, isn't it? On the equatorial plane. So this is the net electric field on the ring. So this is the electric field experienced by the ring. And therefore, what is the force equal to? Force will be equal to E into Q. The electric field into the total charge Q. So simple, look at it. The force will now be equal to KQ by R cube into Q. So that should be the answer to this question. So what is the answer to the first one? First one will have the answer to be equal to B. Equal to this. So that will be KQ by R cube into Q. Excellent, right? Because it gave you the idea of what the electric field due to a dipole is into charge Q, gave me this. That was pretty nice to do with. Second problem. These are all, many of these questions are from the previous year's papers. All right, many of them. I think I made a mistake. It should be Kp, isn't it? Dipole moment P. So I wrote down P instead of P, I wrote down Q. It should be KPQ by RQ. So that's what the option is. That's what the option is. The electric field due to a dipole. Dipole is Kp by R isn't it? On the equatorial plane. So therefore it should be P, KPQ by RQ. Is that matching now? Two charges, 3.2 into 10 to the power minus 90 and minus 3.2 is placed at 2.4 angstroms apart from an electric or to form an electric dipole. It is placed in a uniform intensity of so much. The electric dipole moment is, it is placed in a uniform intensity. Why do I need that? To find out the dipole moment, I don't need. For the dipole moment, what I need is the charge into the separation between the two. Charge is 3.2 into 10 to the power minus 90. And 2D itself, so this entire thing is 2D, is 2.4 angstroms. So 2.4 into 10 to the power minus 10. A typical CET question to do here is this. So you get this to be 7.68 into 10 to the power minus 29 coulomb meter. So look at the answer. Which one basically gives you that? 7.68 into 10 to the power minus 19 is this. So third one should be the right option. Pretty straightforward, simple question. The second one is. So let's look at problem number 3. Problem number 3 is more of a conceptual one. Okay. Third one. You have a charge Q fixed at a distance D in front of an infinite metal plate. The lines of force are represented by. Now look at it. If you actually have a charge Q here, it's a metal plate, and there should be a minus charge induced on this. So this entire thing will now have a minus charge. So how should we expect the field lines to be? Okay, field line will be from positive, it should go to negative. It can't be a straight line because it's not a point charge, it's an extended charge. So the field lines are going to be like this. Now, which one represents the field lines in that way? I think the first one represented like this. It can't be 2 because the field lines are going from the plate to positive charge. That's not possible. Induction will always give you a negative charge there, isn't it? For this case. Straight line is not possible because it's not a point charge. So therefore, first one is the right option. So easy to predict, isn't it? Easy to predict here. The field line direction should be like this. Yes. Okay. So can I go to my next page? Again, a nice question. Let's see how to do this. Fourth one. Now you should all know that in case of conductors, electric field inside the conductor will always be 0. Electric field inside the conductor will be 0. Okay, so you can't have any. So you can't have any field lines inside. You can't have any field lines inside. What does it mean? So 2 can't be the right option. Okay, because it's saying that there's a field inside. 3 can't be the right option because even here there's a field line. So there's only 1 and 4. The tussle is between 1 and 4. Which one to choose? Now, if you have actually a charge particle, a charge conductor, electric field always has to be perpendicular to it. Electric field must be perpendicular to the conductors. If you look at 1, it is not showing you that. Here, electric field is not perpendicular to the surface. Electric field is not perpendicular to the surface. So 1 I can take away. But whereas 4, if you look at, it is coming and hitting the conductor here like this. So this is perpendicular, isn't it? Because it's going towards the radial direction. So 4 is in fact the right option for this problem. Okay, many of them are telling me it is 4, and I think I gave you the reason as to why it should be 4. So the field lines will always be coming out of the conductor in the perpendicular direction. So that's represented well by 4th one. So good. 5th one. 2 identical particles of mass m carrying charge q each. Initially, one of them is at rest on a smooth horizontal plane and the other is projected along the plane directly towards the first particle from a large distance with a speed p. If d is the distance of the closest approach, then this problem actually is a little complicated one, but nonetheless we will try to work it out and see. Okay, if you all are ready for the 5th one, this is how I need to go. This requires some 2 or 3 ideas, so please follow this carefully now. 5th one. Now what does it say? One particle is at infinity, very large distance. Okay, and it started coming down with velocity v. There's another charge somewhere here, charge, which is capable of moving, but initially it is at rest. I think that's given to be capital Q. So let's take it as capital Q itself. Capital Q. And this is at rest initially. Now, as this comes closer and closer to this also will start moving. There is a repulsive force and this will also start moving. Now, whenever you have closest approach, then the relative velocity between the two particles must be 0. Or in other words, v1 minus v2 will be equal to 0, or v1 will be equal to v. Both of them will have the same velocity v. Let's basically take that as something like this. All right. Now, having said this, I can use the 2 things. One is I will use the conservation of energy. Okay. Now, what does the conservation of energy give me? Is that I'll have initially velocity of that is v, so half mv square should be equal to kq square kqq, isn't it? Both of them are same charge, is it? I mistook that. Is it 2 identical charges? Okay. Both of them, in fact, are the same charge q. I'm so sorry. So q square. So it's simply half q square divided by d. That's the potential energy of it. Okay. Plus half m into V naught square for each particle, because they both are particle are moving into 2. But you can know that from conservation of momentum, I can say that mv should be equal to mv naught plus mv naught. Or in other words, you will have this to be a case where v naught will be equal to v by 2. Will be equal to v by 2. And hence I'll have this to be half mv square is equal to kq square by d plus half and 2 has gone already. So v naught square is v by 2. So it becomes mv square by 4. Mv square by 4. So now rearrange the term and get the expression for d. All that I have to do is bring this term to the other side. Then I get this to be half mv square minus 1/4 mv square is equal to kq square by d. What is half minus 1/4? Will be equal to 1/4 itself, isn't it? Will be equal to 1/4 mv square equal to kq square by d. By the way, students, what is k given by? K is 1 by 4 pi epsilon naught. So from that you can find out d will therefore be equal to 4 times kq square by m, or will be equal to 4q square by 4 pi epsilon naught m. So that's the expression for d. Let's see which one will match. For the fifth question, 4kq, third one will basically match. So I have got the expression for the d, separation between the two of them, okay, in this case to be. This is actually on a higher side, but nowadays CET also are asking some tough questions, especially from the past 2 years. They've really changed the pattern of the question itself. So someone was asking me, how many questions come? Which will this question come? Will that question come? All that doesn't matter at all in the competitive examination. This year it may come, next year it may not come. Okay, last year it had come. This year you can actually get a very, very new kind of question. So get ready for the concepts. Don't get ready for the questions. You will be in danger if you get ready for a particular question. Get ready for the concept, then everything will be fine. Okay, sixth question. Two infinite plane parallel sheets separated by a distance d have equal and opposite uniform charge density sigma. The electric field at a point between the sheet is. Dear students, this is something that you can please note down in your summary sheet also. If you have an infinite sheet, okay, which is charged, then you can show that the electric field in front of it is given to be sigma by 2 epsilon naught, where sigma is called the surface charge density. Is called surface charge density. Okay, so that is the expression for the electric field. Now you have two such plates. One where basically is having a charge density sigma. The other one actually has a charge density minus sigma. Both of them, in fact, are kept parallel to each other like this, parallel to each other. Now I have to find out what is the electric field at a point between them. Now the electric field will be given by two things. One is the positive one. It will be in this direction, E plus. There will be another one, E minus, also in the same direction. So the net electric field therefore will be equal to E plus E minus. That will be sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So it will be equal to sigma by 2 epsilon naught. Please don't take the sign on the charge, because I've taken the direction already in the same way, isn't it? And thereby, please don't take the charge on it. And then you get the answer to this in the right way. So sigma by epsilon naught should be the answer to this, because they are equal and opposite. That is why you are getting this. See, the electric field will add up. Okay, let's move on to the next set of questions. Have you all written down this? Can I go to the next set of questions?
Yes, sir.
Yes, sir.
now we have whatever we have done. Any doubts in that? Okay. Seventh question. When 10 to the power 14 electrons are removed from a neutral metal sphere, the charge on the sphere becomes 16 microcoulomb. What is the charge generally? If you remove 10 to the power 14 electrons, so it is n into e. It will be 10 to the power 14 into charge of electron is 1.6 into 10 to the power minus 19. Remember, you have removed the charge, so there will be a deficit of charge. Whenever there is a deficit of electrons, then the body will acquire positive charge. So they should be plus. Hence, I get this to be 1.6 into 10 to the power 14 and so on, and then 19 will be equal to 10 to the power minus 5. Or you can write it as 16 into 10 to the power minus 6 coulomb, which is 16 microcoulomb, and it should be plus. It should be plus. So I get the answer quite easily in this way. Okay. Now, eighth one is a very complicated one. Maybe if we have time, we'll come back and do this. Otherwise, we'll leave this out. Okay. This problem, we'll leave it out. Not to worry. We'll do later. If time permits. Otherwise, we'll do other problems which are more important. It's a nice one, but takes a lot of time. May not be useful for your CET at least. The excess of electron that must be placed on each small spheres placed 3 centimeters apart, okay, with the force of repulsion between the sphere to be 10 to the power minus 19 coulomb. Nice way of asking question, right? You have to remove the excess of electron that must be placed on each one. So you want that to be negatively charged. And what is the force that you are expecting that to be? Force should be equal to 10 to the power minus 19. For this to happen, the force should be equal to kq square, because they are identical. Okay, kq square by r square. So now with this, can we find out what will be the q square here given by? Okay, let's write down that 10 to the power minus 19 into r square divided by k should be q square. Once I know q square, I can find out the number of electrons to be removed. Okay, isn't it? So therefore, I can say that this will be equal to q square is equal to 10 to the power minus 19. R is 3 centimeters. So 3 into 10 to the power minus 4 divided by 9 into 10 to the power minus, so 10 to the power plus 9. I'm so sorry, plus 9. So this is 3 square, isn't it? 3 square will become 9. So 3 square and 9 will cancel off. So q square therefore will be equal to 10 to the power minus 19 plus minus 9 minus 4. All will add up. So it will add up to minus 28 minus 32. 10 to the power minus 32 is q square. So therefore, what is q equal to? Q will be equal to 10 to the power minus 16 of a coulomb. Now, if you want to remove the electron, how many number you should remove? Use this relation. So n will be equal to q by e. Q is 10 to the power minus 16. E is 1.6 into 10 to the power minus 90. So it will go up. And then you will get this to be 1 by 1.6 into 10 to the power 3. What is 1 by 1.6? Any idea? 0.625. This is a value that you should remember, will be useful for your problem solving. Inverse of 1.6 is 0.625. So therefore, the answer to this question will be very simple, 0.625 into 10 to the power 3. So it should be 625 electrons. 625 electrons. So the answer to this question is the third one. 625 electrons should be removed. Okay. I'll go to my next set of questions and let's see what is this about. Again, a nice one. Charge is given to be q by pi r to the power 4. Okay, it's a constant. Be the charge density distribution for a solid sphere of radius r and total charge is q. For a point P inside the sphere R1 from the center of the sphere, the magnitude of the electric field is? Fantastic question. Really, really fantastic question. Now, you know that the electric field inside a sphere can also be written as rho r by 3 epsilon naught. Okay, this also is an expression that is available. Now, if you have this expression here, then let us see what will be the electric field at a distance r. They are telling you that rho is given to be q by pi r to the power 4. That is what is given to us. Okay, r to the power 4. Q by this into r. You will say now r1 divided by 3 epsilon naught. 3 epsilon naught. So therefore, what should be the expression? Look at it. E will be equal to, if you want to write it in the same way, QR1 divided by 3 pi epsilon naught r to the power 4. Same thing here. I wrote down. So that matches exactly with the third one. The answer to the 10th question is a third one. Okay, very simple, very easy to find out. This is an expression that we already know about. Okay. What is the magnitude of a point charge due to which an electric field 30 centimeters away from it has a magnitude of 2 Newton per Coulomb? 2 Newton per Coulomb. You can't get a problem simpler than this, but you should be quick in solving this problem. Okay, that's the idea. Electric field is equal to kq by r square. You have to find out q. Electric field is given to me. So it's E r square by k. Let's substitute each one of them. It is 2 Newton per Coulomb electric field. The distance is 30 centimeters. So write it as 0.3 the whole square divided by 9 into 10 to the power 9. So therefore, Q will be equal to 2 into, this gives you 9 into 10 to the power minus 2, isn't it? Divided by 9 into 10 to the power 9. Goes up. So this will be Q 2 into 10 to the power minus 11. Minus 11. Okay. So the answer therefore to this question is the first one. The first one. Is it okay? I think all of you are getting this. Quite simple. 11th question is obtained like this. 12th question. 12th question. Two identical balls having like charges placed at a certain distance apart repel each other with a certain force. They're brought in contact and then moved apart to a distance equal to half their initial separation. Very nice. The force of repulsion between them increases 4.5 times in comparison with the initial value. The ratio of the initial charges of the balls are. Very nice question, but a lengthy one. Okay, I hope you're all okay with that lengthy problems. Lengthy problems. Let's see how to work on this. F is initially, F is K, Q1, Q2 by R square. Okay, this is F. Then what happens is, I'm going to bring both of them in contact. Then the charge on each of them will be equal to Q1 plus Q2 by 2. This is what bringing them in contact can do. Okay, the charge is going to be this. So the new force, which is 4.5 times the initial value, so 4.5 times F, will be equal to now K, Q1 plus Q2 by 2, the whole square, because there are two charges, both of them are equal, divided by, what have they done with the distance? They have moved half the initial separation, so it should be R by 2, the whole square. So they really made this problem into a problem like this. All right. So which I can write it as 4.5 can be written as 9 by 2. F is equal to, this 4 goes up. So 4K Q1 plus Q2 by 2 the whole square divided by, this 4 is also there. No, this 4 is also there. That will go away. So I can basically write this as by R square. Now take the ratio of the 2. Take the ratio of the 2. Okay. Now if you take the ratio of the 2, you get this to be 9 by 2 is equal to Q1 plus Q2 the whole square divided by divided by Q1, Q2. Q1, Q2. Very interesting. Okay, Q1, Q2. So I can write this as 9 times Q1, Q2 is equal to 2 times Q1 plus Q2, the whole square. It's going to take a long time, but it's okay. It's quite interesting to do. I will leave it after a while and then ask you to simplify and get the answers. Q1 square plus Q2 square plus 2 Q1 Q2 is what the square is. So this is 9 Q1 Q2. Now divide this one by the other. That is 4.5, you keep it. And then you take this down here. This becomes Q1 by Q2. And this becomes Q2 by Q1. And this will be simply plus 2. This will be plus 2. Now put this to the other side. Okay, push this to the other side. If you push this to the other side, you will get 4.5. So this will be 2.5 is equal to Q1 by Q2 plus Q2 by Q1. Dear students, you want to find this. This is something to be obtained. Call this as X. This will then be 1 by X. This will be equal to 2.5. If you do this, you get 2.5x is equal to x square plus 1. In other words, you get x square minus 2.5x plus 1 is equal to 0. Do the quadratic equation, solve this to get x, and that's your value. And you get x to be equal to 2 if you solve this quadratic equation. Okay, solve to get x is equal to 2. So the answer to this question, with all the circles, you will find that it's going to be 2. Answer to this question is 2. Okay, I think with this, let me stop. 3 more problems are there. I'll send the solution for them. Okay, not very difficult ones. You'll find that it can be done easily. So I'll see if possible. I'll also try to do it in my next class if time permits. Otherwise, I'll be sending the solutions for this. Thank you very much. See you all. I've already taken 5 minutes more. I'm sorry about it. Bye bye.
You can leave.
Bye, sir.
You can leave, sir. Please mode. Students mode. Varun.